It's recording, Dr.
Great. So this is our last course with class of new material. I will say that with a caveat that I'll probably end up like figuring out something that I want to reinforce for you guys on Monday, and it might be a slight deviation what we do. But for the most part, there's not any plan to do new content after today. So we'll start out thinking about content for a second, then we'll switch back to logistics. And then after that, we'll go back to working through the material. So if you have not already, check out the clicker question that's posted, and you will see that it's kind of taking up where we left off yesterday, Monday. That's not my dog. It's as loud for you guys as it is for me. But I want us to think about coupled reactions. So we talked about can we drive reactions forward when we have a very powerful reaction and one that is not favored in the way that the reaction is written. So do you want to do a 60-second breakout on this one? Kind of think through it. Sound good? All right. So I'm going to generate the breakout rooms with accepting. All right. Hey, Josh and Tracy, we just sent people to breakout rooms and Alex. So Alex, you should have gotten a request to go to breakout room. Josh, I'm gonna just try to figure out which one to send you to. I'll send you this one. And then Tracy, send you to breakout room 4. You mean to come back so fast, Taylor?
Well, I felt as though it was okay to, I don't know, every time you see that thing, I feel like you want us back. That's why I accidentally clicked it, and I was like, I don't know if I was supposed to stay there the whole 60 seconds or not.
I mean, you can come back whenever you want. It's just sometimes you accidentally click it, I imagine. So
I'm back then.
welcome back. So we only have 6 responses so far. People clicking in, you guys clicking in? Y'all. So as you come back, make sure that you clicked in a response. Hopefully everyone talked briefly to the people in their group and came to a conclusion. Got 13 responses. All right, we're up to 17. That means we're getting close. All right. We have majority, I believe, of our classes on the same page with this. I'm gonna go ahead and close it out. Don't forget units and don't forget the sign. Those are basically the two things that I saw that people forgot. So if we're saying how much can this first reaction drive the second reaction forward, and it looks like we didn't get our little, we're supposed to be, yeah, if I share my screen, if I'm pointing at stuff now. All right, we all back up. So there's supposed to be equilibrium arrows in that reaction, but they did not show up. Basically what we're trying to show here is that if we have these two reactions at the conditions that are shown, the Gibbs free energy there, this reaction can drive the second one forward and still has an excess of negative 15.4 kilojoules per mole. So either we don't need that much and we can use half a mole of the first reaction to drive 1 mole of the second one forward, or we can drive this reaction forward 2 times with the first reaction. So at the end of today's class, I want you to be able to predict which reactions can and cannot push forward the production of ATP or NADH, NH+, versus which ones need those reactants, need those energy sources in order to drive the reactions forward. So we're going to be looking at a lot of different biochemical reactions, specifically in the glycolysis cycle, Krebs cycle. If you haven't already downloaded it, please make sure you have that worksheet, so you have everything there and you can take notes and relate it back to the questions as I have on that worksheet. I also want us, once again, to be able to draw a Gibbs free energy diagram from any one of these values, whether that's the standard potential of standard Ecell potential, equilibrium constant of a reaction, or Gibbs free energy at standard conditions. I want us to be able to predict the spontaneous reaction based on either one of these values at standard conditions. And finally, second to finally, predict spontaneity of a reaction not at standard conditions. And finally, do this conversion between any of those 3 values. And just to touch on the email that I sent out with details about exams 3 and exam 4, I've done a bit of tweaking of what you had for exam 2. So this is a little bit modified. Yes, you will have a majority of your exam on OWL. You will have a good amount of time to do it. Time should not be an issue. Exam 3, I'm opening tonight. So as soon as class is over, in theory, you can go take it right away. The exam closes Monday night at midnight, which means that if you want, it sounds pretty sketchy, if you did want to wait until after class next Monday night, you could, in theory, do it. I'm giving you 3 hours, so that seems like a pretty bad idea. You're going to be cutting it kind of close. Both of the last 2 exams are going to have 2 parts. I think it's really important to me that right before you take the exam, we basically have a conversation. And I say, hey, remember that this is an exam. This is testing your ability to do well in this class. And I want you to perform as well as possible, but I want to make sure it's you and that you're following the same rules you would if you were in a classroom doing this. So the honor contract is a page in a Google form, and you're required to click on that before you take the exam. And it just lists some questions, and it basically says, everything you'd expect. Take this exam as if you were taking it in class. Don't have any outside help, and you're the one taking this exam. You're not going to help anyone else take the exam itself, although I highly recommend studying together. You can have a note card. You can't have polyatomic ions or strong acids or bases on it. And pretty much a standard protocol for taking an exam. You obviously can use the references. I'm not going to give you Ka, Kb values. You're going to have to, just like on your homework, click on the reference button at the top, pull up that reference within OWL. That is an allowable resource, but I'm not going to, you can't go search Google for answers to questions and those kinds of things. If you have any questions about whether something is okay or not, please ask before you take the exam. So the second part in the Google form, the first page is that honor contract. And you'll click through and say, yes, I agree, I agree. Or if you don't agree, then contact me and we'll talk about it. OWL did not have questions that were very good on the Gibbs free energy stuff that we're doing right now. It doesn't align with what we are talking about and how we're working through this. If you'll notice in the homework, there's some questions that are, my questions in the homework focus more on look up the standard potential for a reaction, or a Gibbs free energy for a reaction, a half reaction, and then another half reaction, and then see what the Gibbs free energy is in the total. So it's a bit of a different process than we're doing. So I don't have any of those questions on the exams, exam 3 or exam 4. Instead, I've written some of my own questions, and I have those in the Google form. So they're going to be short response. You're going to have to fill those in, and I'll manually grade those afterwards. Once you finish that whole Google form, I anticipate it probably will take about half an hour. So set aside a little bit of time for that before you take the exam itself. Then you'll be able to go back to OWL and you'll be able to complete the exam itself on OWL. And I think its estimated time is 1 hour and 30 minutes. I anticipate it'll take between 1 and 2 hours for most students to take exam 2. One of the other things I really like is OWL may not give you credit for doing most of the problem right. So I reserve the right to go back through your work and give partial credit. So if you get a question wrong and you get 100% of the credit wrong, I want to have your notes and I want to be able to go through it. So I want your notes for 2 reasons. 1, I want to know that you were the one working on it and I want to see your work. 2, I want to have the possibility to give you partial credit, because OWL does get some partial credit, but if there's something I greatly disagree with or think is unfair grading wise, then I want the ability to go back through that. So I am going to ask that you take notes as you work through the exam, write down your work. And then once you finish the exam, take photos of all of your notes and email those to me. I know email is not the most efficient, but I didn't want another logistic barrier of you trying to upload those photos to Blackboard or something like that. So just send me those in an email. Like we talked about, same resources as if you're taking an exam in class. You have your note card and you can have a calculator, just don't use any programs. Don't use any internet programs. And
Do you want us to take a picture of the note card as well if we use
yes,
one, Dr. Bailey?
good point. I definitely want a picture of the note card. And I mean, I know that this is not the same thing as proctoring an exam in person. I'm completely relying on you being honest and doing things the way that we would if we were in class. But I would like to see the thing so I know kind of what's been happening as much as I can. I don't want to watch you take the exam. I think that that's overbearing, especially for the small class. Exam, so that's exam 3, which is open tonight until Monday night. I do have office hours during that time. So if you want to study on any of this material, please make sure you can attend one of these sessions. If none of these work for you and you want to meet with me, I'm happy to make some more time. So just send me an email, we'll figure out a time. The office hours are tomorrow, 3 to, I don't know why it says 4:50. I was going to say 4:30, but I don't really care. 4:50 is fine. Monday, 3 to 5, and then our class is a review session. Tuesday, 10 to 11:30. And I decided to do Tuesday night late. Will anyone actually go to that? If I do an 8 p.m. review session on Tuesday night? Okay, I see 1 thumbs up. Okay, I don't want to just be sitting here by myself on Tuesday night, but hopefully, since a lot of people work during the days, this might be a useful time. And then Wednesday, noon to 1:30. All of those times, I'll post these slides right after class. They're kind of to help you set up for exam 3, but also exam 4. So I will open up the final exam on Monday morning at basically whatever midnight it is on Sunday night. And it'll be due at the end of the day that our exam was normally scheduled to be completed. You have 4 hours with the online part of that. I don't expect it to take 4 hours. It's probably more like 2 to 2.5 hours is what I'm hoping for. I also have the 2-part honor contract and a couple of questions in Google Forms as well. So same process to be set up. Once you've completed the first part, both of these are accessible in OWL for both exams. So for OWL, you'll see an exam 3 part 1, exam 3 part 2. The part 1 will link you out to the Google form. Part 2 will be in OWL. Same thing for exam 4. Same thing for photos, including your note card, thanks Alex, and same resources that you would use otherwise. Are there any questions on what to expect for office hours, support, or the last 2 exams of the semester?
When's the last time to request credit, no credit?
The university set it up, so it needs to be submitted. I think it's by 5 p.m. on Monday, the last day of class. So by that point, unless you are kind of living by the seat of your pants and taking exam 3 on Monday night, which I really, really don't suggest taking either of these exams up to the time barrier where it ends. I would really advise taking these exams before the deadline, just in case power outage or internet is sketchy or something like that. By the way, if any of that stuff happens, the first thing you do immediately, as soon as the problem happens, email me. Remember that if you open OWL, and you start something, if it crashes on you, you can go in with a different browser or a different computer, and you still should be able to access it. The timer is on their server, it's not on your computer. You can't go back to questions you've already answered, but you should be able to complete the rest of the test. So if you were deciding to do credit or no credit, one, I'd advise you, if you have any questions about it, talk to me. Set up an appointment, either during one of these office hours or another time. It might only take 5 minutes to talk through the options. And then I think you have to decide by 5 p.m. So basically just before class on Monday, whether you want to do credit, if you have a C, a B, or an A, if you think you'll have that, or if you think you'll have a D or an F, you might choose no credit because that won't have any impact on your GPA. So both of them, credit, no credit, have no impact on your GPA. UAMS has talked to the chemistry department, to our chair, and they have said that if you're applying to med school at UAMS, which I know is not everybody that wants to go to med school, but they said that they will be fine with having credit instead of a letter grade for Gen Chem, all of our chemistry courses, Orgo and Gen Chem. So we've been in communication with that one medical school to get that input. So if you think there's a chance that your grade in this class will bring your GPA down, that's when you want to think about taking credit. If you think you're gonna get a D or fail this class, I would probably advise taking no credit. I'm really hoping that we don't have anyone in that second category. I think everyone in this class is capable of passing this class with a C or higher, so let's try to make that happen. Any other questions?
We don't have a primer Monday, right? Because it's just review.
Correct. And there's no post quiz. However, I do have, if you remember the beginning of the semester, there was a survey that I had you take that gave me an idea of where you started the semester. I have a post as well to see where you've ended, so I can see what gains you've made over the course of the semester. That will count in place of your post quiz for week 14. So there will be, it takes about 20 minutes to complete. I need you to complete that by the time you take the final, by the time that end of Wednesday, basically, the final exam's supposed to be submitted. So when you submit that, if you complete it, you'll get full credit for week 14 post quiz.
Is that on OWL?
I will post that link on OWL, yes.
Okay.
Dr. Bailey, did you say that some of the questions on Gibbs Free Energy would be on a separate, would be on something other than the test that we get from Cengage or on the website?
So maybe I should show you all just to put you at ease a little bit of kind of what you can expect. So if we go to, do I have OWL up? Yes. All right. So if I show you OWL here, so this is, your OWL probably looks something similar to this. It doesn't look exactly the same because I'm an instructor in the course. But if you scroll down, you'll see exam 3, part 1, honor contract, and then part 2. So this is the part 2 is your actual OWL exam. Part 1, if you click on that, and you take it, it'll say start, and then you click here to link out. When you do that, it'll bring you to a Google Doc. The first part is the honor contract. And so you have these questions, you need to make sure to trace it to you, and then these are the things you're agreeing to. And then once you go to the next page, which it won't let me do right now, that's where there's a couple of questions on Gibbs Free Energy, K, and Ecell.
Okay, so you wouldn't recommend studying the week 14 homework, I guess, huh?
Yes, 90% of it applies, but there's about 10% where it has you looking up values. So if you're ever gonna take the MCAT, it's gonna be useful to have. It's just not specifically what I'm testing. I'm testing more on, do you understand the relationship between them? Can you convert between K, Ecell, and Gibbs Free Energy?
Okay, so we definitely want to make sure to go back through the stuff that we've done in class and like the POGL activities.
Yes,
A lot of that. Okay.
those are going to be extremely valuable to study from. I'm trying to find my PowerPoint slides. I don't really know. There we go. I would say that there is electrochemical cell on both exam 3 and the final exam. Exam 3 has more focus on the last material. Exam 4 is the entire semester, so there's still some of the things from electrochemical cells and Gibbs Free Energy on there. But the things relating to the Gibbs Free Energy diagrams that I have you draw and the calculations to convert between Ecell, Gibbs Free Energy, and your equilibrium constant, I didn't like the questions in OWL on those, so I made some of my own. And I feel like to have a final exam without any grading on my part would be a joke somehow. So I feel like I should do some of that.
What was the POGIL activity for today?
The one that you attended?
I wasn't there today.
Tripty ran POGIL activity 56 today. It is a really good set of practice problems on the relationship between Ecell, K, and Gibbs Free Energy. All right, if there's any more questions, feel free to put them in the chat window. We can try to answer them as we go, or you can stay after class for a few minutes. So what I want to do now is I want you to enter all of the numbers of reactions from glycolysis, which is this whole list here, that require the input of ATP in order to proceed at standard conditions. So if you think it's 1, 2, 3, type 123, send. And you have this table on the worksheet I've sent you as well.
Dr. Bailey, can you repeat the question? I'm sorry.
So do you see the question in your clicker screen? So it says, which of the following reactions require the input of ATP in order to proceed at standard conditions? And so you can enter whatever the numbers are. So if it's 1, 4, and 9, type in 149, send.
Okay, thank you.
So the numbers should be on your worksheet as well. Couple more seconds to send your answers in. Make sure you hit send in your iClicker app. All right. I'm gonna go ahead and looking at these answers. I'm gonna send you into breakout rooms for 1 minute. Go. Hey, y'all. Do we have Taylor with us? Taylor Arnold? Taylor, can you hear me? All right, looks like we have almost everyone back.
Taylor also just put in the chat that she's here. So
Yeah, I just saw that. Seems like she has this internet connection that's not favoring her being in here tonight. All right, we got everyone back. So can I hear from a group? There's basically two sets of answers for the most part. Either people selected everything but 5, 6, and 9, or they selected 5, 6, and 9. So our question was, which of these reactions require energy to drive them towards products? To drive them, basically, to drive them to proceed means to drive them further towards products. So would anyone like to share what their group discussed and which one they chose? Kind of give us an idea of how we read these plus and minus numbers for Gibbs free energy at standard conditions. Maybe I can ask for Kat to share what your group discussed.
We overall didn't really know, but we did discuss that Gibbs energy and non-spontaneous reactions would be positive. So that's what we assumed. If it was in standard conditions, it was non-spontaneous. So I selected all positive, all the positive numbers. So like 1, 2, 3, 4, etc.
Okay, so can you elaborate when you said that all the positive numbers are non-spontaneous? What does that mean? You can pass if you want, and I can ask someone else to fill in.
I'm gonna go ahead and pass that one.
Okay, does anyone want to describe what non-spontaneous means in this case?
That's kind of where we stopped. We were trying to figure out what it really meant exactly before we came back here.
Okay. Did anyone get to discuss that in their group?
Our group discussed that it means it requires energy.
Requires energy to what?
Move forward.
Great. I think that's a really good description. So in order to move forward, that means to generate more products. It needs an input of energy. I'm really quickly going to draw on a graph here. So if we think about our Gibbs free energy diagram and we talk about this idea that over here is 100% products, over here is 100% reactants. This is kind of the progress, right, of the reaction. And then if you're all the way on the left side of this graph, you have only reactants. If you're all the way on the right side, you have only products. And so if you have a reaction that has the most stable mixture of reactants and products is somewhere over here on the far left side, is that going to have a positive or a negative Gibbs free energy at standard conditions? Anyone want to take a stab at it?
Would it be negative?
Why?
Because it would be going forward.
So careful. What does that little not symbol mean?
Oh, standard conditions.
So that's when Q equals 1. So standard conditions are, if we compare a mixture that we have where Q equals 1, that means we're exactly 50-50 with all reactants and all products. So if the most stable mixture is to the left, we're gonna have a Gibbs free energy diagram that looks like this. Because from our standard conditions, right? Standard conditions is where we're sitting on that energy line, and that reaction is going to fall to the most stable mixture of reactants and products. And if a reaction favors the reactants, then that reaction is not at equilibrium. It's not the most stable mixture. In order to get to equilibrium, the reaction has to proceed in the backwards direction in order to get to equilibrium. So that means that Gibbs free energy at standard conditions is going to be a positive value. That the reaction is non-spontaneous in the forward direction when we're at Q equals 1. To kind of tie together what Tracy was saying there. So if the reaction was spontaneous in the forward direction, we know that Gibbs free energy is negative. And if it's Gibbs free energy at standard conditions, we know that from Q equals 1 to get to the K value minimum, this reaction has to proceed backwards. And the change of this y-axis here is kilojoules per, or whatever Gibbs free energy. So the amount that it has to fall in order to get to the same level as the minimum, this is going to be the actual change in Gibbs free energy, and the sign tells you that it goes to the left. How are we going about that?
So in order for it to go in the forward reaction, it would need the input of ATP.
Exactly. So any of the positive value needs positive delta G naught with a negative G to drive it forward. And that negative delta G value would have to be bigger magnitude wise than the positive. That's so if we go back to our list here, my screen went black for some reason. It's kind of bizarre. We would need to give an input to drive this reaction forward. This reaction is spontaneous in the reverse direction. So I think earlier on we heard someone say that the ones with plus signs are non-spontaneous. And instead of saying non-spontaneous, I think I'd rather have us say that anything with a positive delta G is spontaneous in the reverse direction. So let's talk about the directionality. If we had a delta G naught equals 0, then that's a non-spontaneous reaction, no matter how you define forward and backwards, because it means we're at equilibrium, because Q is equal to K. So that would have a Gibbs free energy diagram where the minimum would be right in the middle. It would just happen to be the Q and K both equals 1. So here we would be able to drive the second reaction forward a whole bunch of times with ATP, because ATP has negative 30.5 kilojoules per mole. And we only need 1.7 to drive that one forward. This one we can maybe drive forward almost twice, but not quite, so we can't really do it. But remember, this is per mole of ATP. So we could just use a little bit more than a mole, and we could drive that reaction 2 moles forward. This one requires a lot more energy. Do these ones need any input of ATP to make them proceed in the forward direction? Nope, they're already going to be driven forward. And then these two down here, we can drive both of those forward. We can drive more of the number 8 than of number 7. And then the last one yields a lot of energy in the production of pyruvate. So the second question, the way I had this one written, which I don't think we're going to do as a clicker question, is which ones of these could be, actually, let's go ahead and I'll ask this question. Looks like, which of these could be used to produce ATP at stations? I'm going to do breakout rooms for 1. And only heads, okay. See some heads now. I'll do 1 minute. I'll close it as soon as I enter a room. I'm just trying to decide what room to send you to. All right, we got everybody back. So we had almost uniform answer to this question. Can I have Verda explain what her group chose and why, and then we'll have a little discussion after that.
We said 569 because they didn't need any additional energy to form anything, so it would just naturally go towards ATP.
Okay, and then I think the question that I asked is, that equation for ATP is negative. So why do we need a negative reaction to produce ATP when that reaction, the way it's written, is negative?
Aren't they both going in the same direction?
True, both of them to get to their minimum are going in the same direction. But why would we need energy for ATP?
Because energy is transferred.
Can you be more specific for ATP?
Might be like a certain amount of the energy of activation that we're looking for, Dr. Bailey.
So these ones actually don't even talk about activation energy. They just
I'm
are talking
confused.
about.
What did you just ask? Did you ask why some of the ones with a negative change in Gibbs free energy might still need the input of energy to proceed?
So we, as a class, selected these three to answer this question. But then I pointed out that delta G naught is negative for this reaction. So would we need energy to answer this question?
Would you need energy? What do you,
So the question is, which of the following reactions could be used to produce ATP at standard conditions?
Yeah,
we
so
need
those
energy?
three wouldn't need energy from ATP.
Right. So why are they able to produce ATP then? If we have a negative delta G for this reaction.
Oh,
Because
because
that's the direction they're going to go.
Because what?
Because they're spontaneous in that direction.
They're spontaneous in this direction.
Yeah.
But the question is asking about production of ATP, which is the opposite reaction.
because the energy released in those reactions is enough to put that third phosphate back on there.
Exactly. So this question is really all about if you change the direction of a reaction, if you have ADP plus phosphate, if we write the reaction in the opposite direction to create ATP, then what's our delta G naught? Is that also favored in the same direction, or is that going to be a changed value?
Would it be positive?
So this question is talking about the production of ATP. That means we're driving a reaction backwards from the way that it's proposed that it should happen. And so if you remember in our looking at the Krebs cycle, we had those steps that went up for the Krebs cycle and energy, and then steps that went down. The steps that went up, we used ATP to drive those steps. When the steps went down, sometimes those would produce NADH, sometimes those would produce ATP. And so it depends on whether we want to store or use energy, which direction we have the reaction go. All right, let's take a look at one last point, which is which ones of these reactions could produce NADH at standard conditions. I'm going to give you 30 seconds to submit your response. Couple more seconds. And closing out. All right, we are all over the place with our answers. Anyone confident in their answer? Want to share? Carter?
Well, I kind of think it's a trick question a little bit
Why?
because none of these have enough energy to produce 1 mole. 1 mole of all of these don't
That's
have
a fair
enough
answer.
to produce 1 mole of NADH plus H.
I don't know that I'd call that a trick question, but yeah, the answer is none. None of the above. So none of these have enough energy to drive the production of plus 61.8 kilojoules per mole at standard conditions for these, all of these at once. And so what we're going to start thinking about is when do we have standard conditions and when do we not have standard conditions? So let's think about inside of cells. That's where all these reactions are occurring, is cellular conditions. So do we think that cellular conditions are very similar to standard conditions that we're using in all these calculations? Go ahead and submit your response. Couple more seconds. Interesting. We have a 50-50 split. What do you all think? Can I get someone to share whether they think standard conditions, what we call standard conditions, are those cellular, is that physiological conditions? I'm gonna switch it up and ask for input from Patrick. What do you think?
I picked it true, but I'm not really sure if I'm right or not.
So Patrick, what are standard conditions? What does that even mean? What does that stand for?
It's a good question.
Without that, we can't answer this.
No, not sure. That's why I kind of guessed on it, because I'm not sure.
Okay. So everything we're doing right now is based on standard conditions or non-standard conditions. So we have to be 100% of that definition. So can I hear from Nick? What are standard conditions?
So I actually said true as well, but for the exact same reason, I wasn't entirely sure.
Why are you not
exactly
Googling this when like when
Oh.
I'm asking it?
I don't know. I'm cheating.
Can someone volunteer that either knows or has just Googled it, Amber?
I said true because standard conditions are 25 degrees Celsius, which is approximately room temperature, and 1 atmosphere, which is about the same pressure as our atmosphere at sea level, which is also kind of living condition for the human being.
True, although most of the reactions that occur in our body are not gas phase. So the 1 atmosphere is a little less relevant. What's the one other standard condition?
1 molar.
Okay, so first question, what is body temperature?
98.6 degrees Celsius.
Get
I don't
out
know
of
what
here. We're not talking about
Kelvin.
Fahrenheit. Does anyone know
I
what it
said
is?
Celsius, not Fahrenheit. I'm sorry, I got that mixed up.
No, you said Fahrenheit, but what is it in Celsius, the scale that actually is useful in science?
Let me calculate it.
Hey Siri, what is?
30.
Really? No one knows this off the top of your head? I feel like this is a really important number if you're doing anything in medicine at all.
37.
Okay. Is that the same as 25? No. Okay. What are the concentrations of things that exist in our body? Does 1 molar seem like a lot or a little? You've done some real lab work before the semester, right? Before we went into COVID lockdown. So you've seen molarities. And when we did high molarity concentrations, like it was like 0.5 molar or 0.25 molar in lab. So no and no. Our bodies are not at standard conditions and far from it. So standard conditions are just something that we use as a reference point because we can compare. And so there's a very wise person who once said, cellular conditions. So it's nice to have a reference point. It's nice to say that my house is 125 feet above sea level. That tells me how high I am compared to something that we know and we can all reference, right? Amber's house might be 600 feet above sea level. It doesn't really tell us how far we are from the center of Earth or from the edge of the atmosphere. It tells us relative to something that we're all using as a standard. That's what standard conditions are. They're just a way to say, okay, well, compared to something that we all can talk about, I'm a lot higher, a lot lower, or different. So these standard conditions are not what we're expecting to see in reactions. So we have to have a way to calculate Gibbs free energy at any condition if we look up the standard conditions. So we're going to go back to these equations that we looked at last class. So we looked at the equation Gibbs free energy is equal to RT ln Q over K. You can rewrite that as RT ln Q minus RT ln K. And we said that Gibbs free energy at standard conditions, or Q is equal to 1. So that first part becomes 0. So we have the simplified condition at standard conditions. Gibbs free energy equals, at standard conditions, is minus RT ln K. So remember we did that last calculation. If we have K, we can find delta G. If we have delta G naught, we can find K. So now what we're going to do is we're going to utilize that relationship to simplify this equation if we know what delta G naught is. So we can go in a book, we can look up this value for a reaction, right? We just have that whole table. And if you get to biochemistry class, you're gonna get so sick and tired of these standard Gibbs free energy values because you're gonna know to look them up. That's the only thing you're gonna look up for a big part of the semester. So if we look these guys up, this minus RT ln K is actually part of the delta G for non-standard conditions. So we can substitute this part for delta G naught. You follow me on what I'm doing there? Any questions on that? So our simplified version of that equation is simply, let me go forward, come on. If we plug it in, it's delta G at non-standard conditions. Any condition, so any Q, not just a Q of 1, which is standard conditions. So we can use RT ln of Q, whatever our Q is, as long as we know our concentrations, we can find Q, plus delta G naught. So there's one additional component that you all probably will benefit from working through. And this simplified version of the equation can now be tethered to the electrochemical potential of a cell. So we're not going to talk about where these numbers come from, or these equations come from, but these are a way to relate Gibbs free energy to electrochemical potential of a battery or of a cell. So can we rearrange that Gibbs free energy at non-standard conditions to include Ecell now? You'll feel comfortable doing some substitutions. So we can either switch out the ones in red, or we can switch out the ones in purple, and we can make other equations that now relate Gibbs free energy and Q to our electrochemical potential of a cell if it's something that transfers electrons. So we can do that on both sides if we wanted to. So I substituted delta G for the non-standard conditions, delta G naught for the one at standard conditions. And then if we solve for our electrochemical potential of the cell, we end up with an equation that's called the Nernst equation. So the Nernst equation is a rearranged version of this top equation, but we're using these definitions of Gibbs free energy related to electrochemical potential of the cell. So this says that if we know the standard conditions, remember all those calculations we did for the voltage of a cell, of a battery? That was these values that we're calculating, the standard electrochemical cell potential. But then if it's not at 1 molar concentration of everything, we have to know what Q is. If we know the temperature, our gas constant, this N is the number of electrons that are transferred in the reaction. And for the primary, probably calculated as F as well, right? Faraday's constant. So with all of these combined, we can calculate what the actual potential of an electrochemical cell is that are at non-standard conditions. So let's take a look at applying this. Let's take a look specifically at this equation down here, which is one of the ones we were looking at in our list of glycolysis reactions. So we're generating NADH and H+ by converting glyceraldehyde 3-phosphate to 1,3-bis-phosphoglycerate. All right, so we're going to take that reaction, and I want to know whether you would expect that reaction to be able to produce NADH and H+, and we're going to do an A, B, yes, no. I don't have it listed up here, but A is for yes to this question, B is for no. A is for yes, B is for no. Couple more seconds. All right, we have a majority of the class is answering no. We're not going to be able to drive this reaction forward. Can I have someone explain their answer? Why are we saying no? This reaction cannot drive the production of NADH. Can I hear from Gabby? If you answer that, or if not, share your answer, please.
I picked no, but I'm still not exactly sure why. Like, I know that at standard conditions, like the Gibbs Free Energy is less, so I know that probably ties in, but I don't know how to explain.
Okay, appreciate that. Aislinn, what did you choose and why?
I chose B also, but I had the same thinking from the last question, but that one's G naught and that one's not G naught, so I don't know.
Amazing how confusing that sounds when you say it out loud.
Yeah, sorry. That one's at standard conditions and this one is not.
Fantastic. Okay, no one answered C, and you could have been like, we can't tell, because I never said everything's at standard conditions here. So the answer could have been, well, this one at standard conditions can't drive the production of NADH at these conditions, whatever they are, but we don't know what they are. So let's talk about specifics of, if we know what this is at standard conditions, let's take a look at non-standard conditions. So go ahead and turn to page 2 of your worksheet if you haven't already. And let's try to calculate whether this could happen. And to do that, we're going to calculate Gibbs free energy at non-standard conditions for this reaction here. So we're going to do this, we're talking about now in the brain. We have both glyceraldehyde 3-phosphate, it's at 10 micromolar, and we have 1,3-bis-phosphoglycerate, and that's at 0.5 micromolar. So I want you in groups to calculate Gibbs free energy, knowing the standard conditions are this. I want you to figure it out what it is at non-standard conditions. So I'm going to send us into groups, and we'll try to start working through this. We'll take about 5 minutes or so, or less if we figure it out quicker. Welcome back, everybody. All right, so I'm trying to keep an eye on the clock, make sure we get a chance to practice this and look at how it all fits together. So I think pretty uniformly, we got to the point where everyone in the class was saying, okay, if we know Gibbs free energy at standard conditions, we can find it at non-standard conditions using the equation that we just talked about. Does that sound reasonable? So then the question is, what would be a reasonable value of the product? And of this, what would be a reasonable answer, and how do we find that? So maybe another question that I should have asked is, draw a Gibbs free energy diagram of this reaction. So if we draw a Gibbs free energy diagram for this reaction, this is all reactants on the left, this is all products on the right. Delta G is our y-axis. Where is the minimum of this reaction going to lie, knowing our delta G naught is equal to negative 55.5 kilojoules per mole? Lauren, any thoughts on what the Gibbs free energy diagram would look like?
No.
All right, who can help me out here? Carter?
It'd be close to the reactant side, wouldn't it?
The minimum is close to the reactant side, is that what you're saying?
I think so.
So let's take a look at two components. One is that we're saying from standard conditions, right, that delta G naught, we have a negative value of delta G. So if we're at Q equals 1, we're at standard conditions, we're right in the middle, right? That's what that delta G naught means. This reaction is going to proceed in which direction to reach the minimum? What does a negative value tell us about the direction to reach the minimum?
It's going towards the products, right?
Absolutely. So this reaction has a minimum that's closer to the product. So this reaction has our most stable mixture of reactants and products is over much further towards the products than it is reactants. That's why from standard conditions, we have a negative sign, meaning the reaction proceeds in a forward direction to reach that equilibrium. And remember, that value down there is where we would find our equilibrium constant K. So then what's a reasonable answer for this question? We're saying that in this question, we started, our comparison point is delta G naught, so we're at standard conditions. We're saying that that has a negative delta G. And then we're saying instead of a Q equals 1, what is our Q value for this problem up here? Did anyone calculate just Q by itself? At non-standard conditions with these concentrations here?
0.05.
At 0.05.
Okay, so where is that on that curve? Are we left of the middle? Are we right of the middle? Taylor's showing to the left. I agree. We have many more of the reactants than we do the products. So we're somewhere up here. So the question is delta G, should it be a bigger magnitude, a smaller magnitude? Should it be same sign or a different sign? These are all questions that I have written into my exams. So if you're given delta G naught, if you're given delta G, if you're given K or Ecell, I need you to be able to say that we're on this side of standard conditions. It changes the sign or the sign stays the same, and the magnitude changes or stays the same. So in this case, if we're looking at delta G now in these conditions, is delta G changing sign or staying the same sign? Verda says the same sign. I agree. To get to equilibrium, the reaction still has to go in the forward direction. Is the magnitude, is the number going to be bigger than 55.5 kilojoules, or is it going to be less? See some pointing up. I agree. So this is going to be bigger of a value than our standard conditions because we went further up and we have to go the same direction to get to equilibrium. So the sign stays the same, the magnitude should get bigger. So I will ask those kinds of questions on exam. Sometimes I want to ask you to calculate it. I'll just ask you to say what happens to the sign, what happens to the magnitude. Okay, so if we did our calculations, we can find our Q is our micro. Honestly, I know that you hate micro, and I know that you should be using micro because you will in future classes and in work, but micro means 10 to the negative 6. What's important here is the ratio. It's a 1 to 20 ratio. At standard conditions, we had a 1 to 1 ratio, but for this one, we have a 1 to 20 ratio. So if we put that all in to our original equation there, we have our joules per mole. So we have kilojoules, 10 to the third joules per mole. We have our gas constant, which is 8.314 joules per mole Kelvin. We have our temperature is not standard temperature, right? We're at body temperature, which is 37 degrees higher than 273. So it's 310 degrees Kelvin. And if we use all those values, I found negative, and I messed up. I realize that right now. I messed up here because this should be our negative value. I don't know if anyone saw that I missed that little negative symbol there.
Yeah, I was confused for a second, but I'm glad you clarified that.
You should harass me, Alex, if you see I make a mistake like that. One of our last chances to do it, but you're welcome to anytime. All right, so I found that we had 63.2 kilojoules negative delta G at these conditions. So going back to original question, can we still drive, or can we drive the formation of NADH and H+ with this reaction in these conditions? Yes. I see Taylor nodding her head. So we have now more energy than we need in order to drive NADH and H+. So this reaction, if we just change the concentrations, it gives us more potential energy or chemical energy that we can use, and we can drive reactions forward that we otherwise weren't able to. So what I wanted to also point out is that maybe we didn't want to use that equation. Maybe we wanted to be really fancy and calculate Ecell. So I had another question in here where we could have calculated Ecell. So with the equations we've looked at before, how would we calculate Ecell for this reaction? Or our equilibrium constant K? Those are two other things that we need to be able to calculate given delta G naught. I'm looking at the clock and we only have about 1 minute left of class. So any answers, any suggestions?
Well, we use the equation delta G naught equals negative NF E naught cells. Oh.
Say again, delta G naught equals?
Negative NF E naught.
Yes. So we can calculate the electrochemical potential at standard conditions. And then that equation that I referred to as the Nernst equation uses that relationship to then calculate our actual electrochemical potential. Faraday's constant, that's, what is that, 96,485 joules per mole times volt. The number of electrons, I think in this one I described in the last problem that we have 1 electron being transferred. And so we could calculate our standard electrochemical potential. And I think I actually have those written out here. So let's do that show that really briefly. So this first equation here is the long version of it that we could calculate. The second one is the one that Taylor just mentioned to us. So we can calculate electrochemical potential of the cell at standard conditions from Gibbs free energy at standard conditions. We can just rearrange this equation to solve for the standard potential of electrochemical cell. And I found 0.575 volts is the standard potential of this chemical reaction. We can then use that back in this equation here. What is our Q value again that we had for this one? 0.05, does that sound right?
Yes.
We know our gas constant. We know the temperature. We know it's 1 electron transferred. We'd have to know how many electrons or else we can't answer this. And we know Faraday's constant. So we could plug all those things in this giant equation. It's just bigger here than up there. And then we see that the electrochemical potential is actually a larger potential for this, which makes sense. It was a bigger delta G than delta G naught. It means it has more spontaneity. It is further from Ecell of 0 would mean it's at equilibrium. There's no reaction that can take place. So we're further away from 0. So this is the kind of calculation that I want us to be able to do. How would we calculate, if I asked you to calculate our equilibrium constant, how would you calculate K with the information that we have? Would that be possible? Would we use delta G or would we use delta G naught to calculate our equilibrium constant K? Standard conditions or non-standard conditions?
Standard.
I agree. So if we had our delta G naught equals minus RT ln K, we have delta G naught, we can solve for K. We just use this equation to solve for Ecell. And one thing that I just kind of skipped over really briefly was that if we have Ecell, we can also find K through this relationship here. And at the very end of that last slide, let's just say that you didn't know what you're doing and you used this equation to start with instead of the one that we used on the last slide to calculate delta G at non-standard conditions. Once you have your Ecell at non-standard conditions, you could go back and use this equation and you could have backed out delta G at non-standard conditions. It would have been a really long way around, but all of these relate to each other. And so we could have found the same delta G at non-standard conditions by doing these calculations. All right, so that is where we're kind of ending the semester. Is I want you to be able to, with any one of these 3 values, I want you to be able to calculate the others at standard conditions and then know how to go from standard to non-standard conditions and know if those numbers make any sense. So if this class was a bit rough for you, 2 things you should know. 1, I typically do these last 2 classes in one day, as Tripty can attest to, because it's the end of the semester and we usually get cramped, and I pulled out some stuff at the end so we could take 2 days to do this. Second thing is, don't worry if you feel overwhelmed by all this. We have office hours, a lot of them over the next week. If you can't make any of those, then please give me a shout and we can chat through them. The POGO activity 56 that Tripty worked through tonight was on this topic as well. So even if you went through it tonight, you might want to go back through it and see how these things all relate and how you can calculate the relationship between them. All right, I'll be happy to stick around if you have any questions, but that's it for us tonight. Thanks for your patience, and I'll see you office hours or Monday.